This lecture is in continuation of the previous lecture on measurement of quantities. I will proceed here further. So, next was electrical units. Electrical units. Current, as all of you know, is usually measured in ampere, and in short it is denoted by A. In solids, the flow of current, it consists of flow of electrons. In electrolytic solutions, most of the current flows by movement of the ionic species. Now, 1 coulomb is the unit of charge, and that means this is flow of 1 ampere per second, that is what 1 coulomb is. Now, SI unit of electrical potential is volt. I think all of you know, and volt, this is the potential, volt is the potential in which a charge of 1 coulomb experiences a force of 1 Newton. Now, this is what about the volt. Now, as also you know that SI unit of resistance, do you know what is SI unit of resistance? That is ohm. Now, ohm is defined as the resistance, it is just a basic and elementary, just I am reviving, is the resistance which permits flow of 1 ampere current, 1 ampere current under the potential difference of 1 volt. Potential difference of 1 volt. That is how you define the ohm. Now, some basic equations of electric flow, as some basic equations for electrical flow are, that is volt, as all of you know, that is equal to resistance into current, that is I. Now, P, that is power, that is equal to I into V, that is also equal to I square into R, and W, that is the energy which is measured in joules, that is T into P, that is equal to I square R into T. Now, here T, that is equal to time, W energy measured in joules, and P is the power. Now, another important unit is that a Faraday is 1 mole of electrons, 1 mole of electrons. 1 Faraday, that is equal to 96,500 coulomb. Now, also it should be known that 1 Faraday on passing in an electrolyte will discharge 1 gram equivalent of ions. That is, the liberation of 1 gram equivalent of any metal consumes 96,500 coulombs of electricity. These are some of the basic units and dimensions for electric flow. Now, let us consider, say, how many gram moles of Al3 plus, how many gram moles of Al3 plus. You know, aluminum has 3 charges, ions could be discharged in 1 minute by 1.9 into 10 to the power 4 ampere current if no loss of current occurs. No loss of current occurs. It is a very simple problem. That means, if you pass 1.9 into 10 to the power 4 ampere of current in an electrolyte in order to discharge Al3 plus to aluminum, how many gram moles of aluminum will be deposited? Very simple. So, now let us calculate, say, in 1 minute, how much current will flow? The current will flow 1.9 into 10 to the power 4 into 60 amperes. That much current will flow. Now, you know 96,500 say coulombs will deposit the molecular weight of aluminum is 26.98 divided by 3 gram of aluminum. That is what the definition of this. So, therefore, this will be coming approximately equal to 1.14 into 10 to the power 6 ampere. That means, you can straight away say this 1.14 into 10 to the power 6 coulomb will deposit around 106.2 gram of aluminum, and gram moles of aluminum, gram moles of aluminum would be 106.2 divided by 26.98, and that will be equal to 3.8 gram moles. That is a very simple question. Now, let me try another problem. For example, if you consider again very simple problem, say a 2.5 volt, a 2.5 volt potential drop is applied down a circular bar of 0.15 meter radius, which is 2.5 meter long, 2.5 meter long, and has a resistivity of 1.8 into 10 to the power minus 6 ohm. What is the magnitude of the current? What is the magnitude of the current? Now, I will request you to solve this problem on your own. All that you have to calculate the area of the bar and find out the resistance and then find out the current. So, answer for this problem that is current, that comes out to be equal to 3.14 into 10 to the power 4 amperes. So, try yourself and get a feel of the calculations on electricity. Now, with this I had finished the conceptual part of the lecture on measurement of quantities. Now, I will try to give you exercise with some solved problems and some unsolved problems. Now, let us see the exercises. These are the exercise on units and dimension. I will read first of all the problems, and then I will solve, or I will give the answer one by one as I will proceed. Problem 1, convert the value of universal gas constant into A CGS and B MKS units. Given R, that is equal to 82.0578 centimeter cube atmosphere gram mole to the power minus 1. So, what is involved in this problem? In fact, you can see the value of R in CGS and MKS units in any standard book, and you can straight away write down the answer, but that is not the objective of this particular problem. What I would like, that from given the dimension of R centimeter cube atmosphere gram mole to the power minus 1, you should be able to derive by suitable multiplying factor on your own the unit of R in CGS and MKS system. That is what the intention of this particular problem. I know that several books give the value of R in different dimensions, you can see and you can write, but that will not serve the objective of giving this particular problem. You have to derive the units from fundamental units, that is mass, length, time and temperature. That is what the intention. Problem 2, the MEC power of a black body, that is all of you know, is sigma T to the power 4, where W is BTU per hour per feet square is given and sigma is given to you in this unit. So, what is the value of sigma? In A, calorie per second per centimeter square, degree Celsius to the power minus 4, B, in calorie per second per centimeter square Kelvin to the power 4, and C, joule per second per meter square Kelvin to the power 4. So, again you have to derive this unit from the basic units, because as I said in my first lecture that all the units can be derived from the fundamental units, that is what the thing. Third, thermal conductivity of aluminum at 32 degree Fahrenheit is 117 BTU per hour feet degree Fahrenheit. Find the equivalent value in calorie per centimeter per second degree Celsius. Now, here again you can straight away see the book, multiply by the conversion factor and you will get the value, but that is not the objective of this particular exercise. The objective of this particular exercise that you find out by suitable factors the units in calorie per centimeter per second degree Celsius. Convert 360 millimeter mercury to Newton per meter square and pound per feet square. Fifth, the pressure in an evacuated vessel was recorded as 1.2 dynes per centimeter square. Express this value in microns of mercury at 25 degrees Celsius. Now, you must have noted here that I tried to give the problem in all the 4 basic system units, that is CGS, MKS and FPS, all that you must be conversant with the interconversion of units from one system to another system, that is also an important thing. Now, problem number 6th, a slurry stream containing quartz is diverted into a 1 liter cane, that is a slurry is flowing, you have taken a 1 liter cane and into this you have diverted that slurry. Time taken to fill the cane is 8 seconds. The density of the slurry and quartz is 1400 kilogram per meter cube and 2650 kilogram per meter cube respectively. Calculate A, percent solid by weight, and B, mass flow rate of quartz within the slurry. So, this problem is very important when we proceed to the material balance in metal extraction and refining. Problem 7, 2 slurry streams enter a pump. There is a pump and 2 slurry streams they enter into it. One stream has a flow rate of 5 meter cube per hour and contains 40% solids by weight. Other stream has 3.4 meter cube per hour flow rate and contains 55% solids by weight. Density of solid is 3000 kilogram per meter cube in both the slurry streams. Calculate tonnage of dry solids pumped per hour. So, these are the problems that are given to you for the exercises. Now, I will discuss one by one, and where I will see that I should give the solution, there I will give, otherwise I will give the answer and proceed to the next. So, let us take the solutions of the exercise. See, number 1, the conversion of units, what I meant. For example, you have to convert in CGS units. So, you are given R, that is given to you 82.0578 and it was given in centimeter cube, atmosphere, gram mole, degree Celsius. Now, we have to obtain in, we have to get in CGS unit. So, all that you have to do, that is you have to interconvert it, and I am straight away giving the answer. The answer will be 1.986 calorie per gram mole degree Kelvin. That is the answer for part A. Now, similarly, for part B, you have to derive in joule per kg mole degree Kelvin, and you can see that is given 82.0578 0.0578 into pressure 1.01325 into 10 to the power 5, that is in Newton per meter cube, that has become, and if we divide here say meter square into 10 to the power 6, because I am just deriving from here. So, that is why this thing coming into 10 to the power 6 kg mole. So, and degree Kelvin is already existing there. So, that is equal to 8314 joule per kg mole degree Kelvin, and that is the answer for B. So, now let us proceed to the problem number 2. Say problem number 2, the MEC power of a black body. So, I am giving you the answer, you try to derive the answer for part A, that is equal to 1.35 into 10 to the power minus 4 calorie per second centimeter square degree Celsius to the power 4. Answer for B, that is also 1.35 into 10 to the power minus 4 calorie per second centimeter square degree Kelvin to the power 4. Now, the answer for C, 5.669 into 10 to the power minus 8 joule second meter square degree Kelvin to the power 4. So, that is what the answer for question number 2. The answer for question number 3, you have to convert thermal conductivity, and the answer is 484 into 10 to the power minus 3 calorie per centimeter degree Celsius per second is the answer for third. Now, answer for question number 4, you have to convert, you can straight away try, I will give you the answer. A part is 47,995.2 Newton per meter square, and B, the answer is 1002.4 pound force per feet square. The answer for fifth, where you are required to convert 1.2 dynes per centimeter square into microns of mercury. So, the answer is 1.596 microns. Now, let us try question number 6. Now, question number 6 says a slurry stream containing quartz is diverted into 1 liter can and it takes 8 seconds to fill the can. The density of the quartz and that of slurry are given. You have to calculate percent solid by weight. You record in my first lecture I derived how to calculate weight percent solid. So, straight away I will be using this formula and I will solve this particular form for you. So, for A part percent solid you recall I am writing the formula again, that is equal to 100 rho slurry rho m minus rho w, that is equal to rho m rho s minus 1000, where rho s is the density of the solid, rho m is the density of the slurry. This already I have given. So, what I will do? I will straight away substitute the value. So, 100 into 2650 into 400. So, density of water, as we have to take around 1000 kilogram per meter cube. So, that come divide by 1400 into 1650. So, that straight away gives you the answer 45.88%, that is the answer for the part A. Now, the part B, it asks you mass flow rate of quartz within the slurry. Now, B part, to calculate mass flow rate of quartz within the slurry, because this slurry is required to be transported by pump from one place to another. So, you have to know the what is the say mass flow rate of quartz, because quartz is the most important. So, we have derived the formula mass flow rate M, that was, if you recall, F into rho m into percent x upon 100. So, all that I have to substitute the value and I have to get the answer. So, if I substitute all these values, because you know F is the mass flow rate, that is 1 upon 8, 1 liter, it takes around 8 seconds. So, if I convert in the units, then it will come around 3600 upon 8000, that will be in meter cube per hour. Now, all that I have to substitute the value. So, that will be equal to F is 3600 divided by 8000, density of the slurry is 1400 and percent x, that is given to us, that is we have calculated 45.88, of course, divided by the 100. So, this mass flow rate of the slurry, that comes to equal to 289 kilogram per hour. Now, for example, if it takes 7 seconds to fill up the 1 liter of cane, then mass flow rate of the slurry naturally will be 330 kg per hour. Just a side problem that I thought I will give you. Now, the same M you can also calculate, you know, we also derived an alternative formula, that is M in kg per hour. In case you do not want to calculate percent x, then straight away you can use it, that will be equal to F into rho s, rho m minus 1000 upon rho s minus, you calculate again, you will be again getting the answer 289 kilogram per hour. That means, well, here this problem was consisting of a sequentially, that is, first you calculate percent x and that calculate kilogram per hour. Now, head you are not required to calculate weight percent solid, straight away it has been asked that calculate the mass flow rate of the quartz in the slurry, then you have to use this particular formula, all that you have to replace the percent solid in terms of the quantities which are given to you, that is the only difference. So, that is the an alternative way, or whichever way you want to think. Now, the last problem of this particular thing, that is the 7th problem, it is again a very interesting problem. Many times two different flow rates, they are required to be transported. The two different flow rates, they may have different densities and different percentage of solid. Both of them pass to a pump and then the pump discharges a single stream. So, this problem is that two slurry streams enter a pump and the flow rate of both these streams are given, as well as percent solid is also given. So, now you have to calculate tonnage of dry solids pumped per hour. Now, this particular problem has a significance, because in all mineral processing operation you are required to handle the slurries. Slurry means a solution of solid in water. A large amount of solids in water are being handled for concentrating operations. So, many times you require to designate what is the capacity of the pump you require. For that you must know how much amount of solid will be transported per hour, and that particular problem is addressed to that particular issues. So, here again, well, I will proceed in my style, but I will request all of you to please do yourself develop a new method of solution. Well, what I will be solving, I will be first of all calculating the density of slurry in both these streams, and I will proceed that way. So, I have given already the formula for weight percent solid, the interconnection between weight percent solid and the densities, that is already known to you. So, I am straight away substituting that those values. So, in one slurry you have 40%. So, 40 that is equal to 100 into 3000 into rho m 1, that is density of slurry 1, minus 1000 divided by rho m 1 into 3000 minus 1000. So, this way I can calculate now the value of rho m 1 density, that is equal to 1364 kilogram per meter cube. This is for slurry 1. Now, here itself I can calculate the mass flow rate of slurry stream 1, that is m 1, that is equal to 5, is all the values are given, into 1364 into 40 by 100, and that is equal to 2728 kilogram per hour. This is the flow rate, mass flow rate of slurry stream number 1. Now, let me calculate for slurry stream number 2. Slurry stream number 2, I will proceed the same way. So, again I calculate the density of slurry 2. So, I will be calculating 55% solid, that is given 100 into 3000 rho m 2 minus 1000 upon rho m 2 3000 minus 1000. So, if I solve for rho m 2, so from here I will be getting density of slurry stream 2, that is equal to 1579 kilogram per meter cube. So, I can calculate now mass flow rate, that is m 2. M 2 I can calculate, the flow rate is given 3.4 into 1579 into 55 by 100. So, that will be equal to 2953 kilogram per hour. So, tonnage of dry solids, pumped per hour, that will be, I have to sum total both of them. So, it will be 5.681 tons per hour. So, that way I have solved all the problems of the exercises. Though I have given the solution, I have not given the solution with the idea that you just copy. I would like and appeal to all of you, please solve yourself, and solution you only see in case you are stuck somewhere. I think you can solve the problems. So, with the exercises, the lecture on measurement of quantities, I think I am able to give you the sufficient information on units and dimensions. Now, I will proceed to the next lecture, and that is on stoichiometry. Now, many of these material balance problem that arise in metal extraction and refining, they can be solved either from a knowledge of atomic or molecular weights, molecular weights of reactants and products, participating in a balanced chemical reaction. That is, if you have the reactants, you have the product, if you know the atomic masses or the moles, you balance the equation, and many of the information can be obtained from the atomic masses of the reactants and products that are taking part in a reaction by making a balanced chemical equation. That is, from the law of conservation of mass, the moles which are participating, the similar number of moles must also exit. That is the important. Second, mass of compound contained in a given volume of gas. Now, say this stoichiometric can be used to develop other relationship also, as we see in the course of the lecture. Now, some of the basic which probably you know already, just I am giving here for the sake of completion of the lecture. Basic atomic mass or molecular mass, for example, zinc, it is 65.34, you may use approximately 65 also. Say iron, you can use 56, or to be more precise 55.85, copper 63.54, or you can use precisely also 64, zinc you can use a 65. Now, for example, if you want to calculate the molecular weight of zinc sulphide, so zinc sulphide will be equal to 65.34 plus 32, that will be equal to 97.34. Now, remember this unit is kilogram per kg mole, or approximately you can also put that is 97 kilogram per kg mole per kg. That is what the similarly another example, if you want to have say Fe2O3, multiply, that is 112 plus 48, that is equal to 160. You can write either kg per kg mole, or you can also put it 160 gram per gram mole, whichever way the problem is. Now, the chemical equation Let us see what we can do from writing down the chemical equation. In fact, a balanced chemical equation is based on the law of conservation of mass. Law of conservation of mass. That means, number of atoms or elements in the product, that is equal to number of atoms or elements in the reactants. It is very simple. Now, sometimes it is also important to write down the state of the reactant that are taking part in the equation to avoid the confusion, because many times you have one solid plus gas, that gives you solid plus gas, that is okay, but in case of solid plus gas, if it gives liquid, then it is easier to understand the chemical equation and hence to calculate properly. So, that means, it is also advisable to write state of the elements, state of the elements participating in a reaction in the parenthesis. Now, for example, say if we take, say for example, if we take 2 Fe, that is solid, that is the way you write, plus 3/2 O2 gas, that is equal to Fe2O3 solid. Now, this habit of writing the chemical equation utilizing the state of the element is very helpful for various thermophysical and thermochemical calculations in thermodynamics, because when there is a state change, then the latent heat and all those things are involved. So, if in the equation those states are represented, you will be safe in your calculation. Now, similarly, for example, if I write now Cu2S, typically the copper sulphide for production of copper, that is in the liquid state you have. So, you write in the liquid plus it is oxidized with oxygen, which is in the gaseous state. So, you get now 2 Cu, that is liquid, plus SO2. Now, let us consider this balanced equation, that is production of copper by oxidation of copper sulphide. We see that copper sulphide is in the liquid state, oxygen in the gaseous state, and copper in the liquid state, and SO2 again in the gaseous state. Now, this is a balanced chemical equation. Now, from this balanced chemical equation, one can derive so many information. Now, say what information we derive from a balanced chemical equation, I am using this particular example. Now, this particular equation says that 1 mole of Cu2S, 1 mole of Cu2S combines with 1 mole of oxygen, combines with 1 mole of oxygen and produces 2 moles of copper and 1 mole of SO2. Now, I simply mentioned in terms of the moles that are taking part. Now, second information it also says that 2 moles of copper, 2 moles of copper are formed from 1 mole of Cu2S, 1 mole of Cu2S. That is also the information you get. Also, you can see that 1 mole of sulfur in Cu2S gives 1 mole of SO2, gives 1 mole of SO2. Also you can see here, fourth, 1 mole of oxygen forms 1 mole of SO2, You can also write also in terms of gram if you wish. So, you can see from this equation that 159.08, or if you write say copper molecular weight 64, then that is equal to say approximately 160 gram or kilogram of Cu2S gives 128 gram or kilogram of copper. So, similarly, you can obtain various information from the balanced chemical equation. Now, let me illustrate it by giving a suitable example. Now, let us calculate say how many moles of SO2. You see how easier it becomes to write a balanced chemical equation and to proceed the calculation, because from the balanced chemical equation you can derive so many information. Let us see now how many moles of SO2 are produced when 1 ton of copper matte. In fact, copper matte is a liquid solution of sulphide, that is it contains Cu2S plus FeS, that is what the matte is. 1 ton of copper matte containing 60% Cu2S and rest and 40% FeS. So, that is what we have to find out, how many moles of SO2 are produced. Now, here say FeS is converted to FeO and SO2, Cu2S is converted to copper liquid and SO2. Now, we can write down the balanced chemical equation. Now, say for 1 mole basis you have Cu2S plus O2, that is equal to 2 Cu plus SO2 and FeS plus 1.5 O2, that is equal to FeO plus SO2. Now, we have to substitute the different moles which are involving. So, we have 1 ton, that means you have 600 kg Cu2S, that is equal to 3.77 kg moles, and 400 kg FeS, that is equal to 4.55 kg moles. So, I have to write down now this equation 1 and this equation 2 by utilizing the moles which are participating in the reaction. So, if I do that, then I will be getting say 3.77 Cu2S plus 3.77 O2, that will be equal to 7.54 copper plus 3.77 SO2 and 4.55 FeS plus 6.8175 O2, that will be equal to 4.55 FeO plus 4.55 SO2. Now, you can straight away find out the moles of SO2 that are forming, because you have written the equation in a balanced form. So, straight away the 1 ton of copper met, which was containing 3.77 moles of Cu2S and 4.55 moles of FeS, will give you the moles of SO2, that will be equal to 3.77 plus 4.55, and that is equal to 8.32 kg moles. Now, from here onwards you can calculate anything here, moles of SO2. You can also calculate weight of SO2. If you are interested weight of SO2 in kilogram, what you have to do? You have to multiply 8.32 into molecular weight of SO2 is how much? 32 plus 32, 64. So, that will be weight of SO2 in kg. You can also calculate volume of SO2. Volume of SO2, that will be equal to 8.32 into 22.4, that will be meter cube, expressed at 1 atmospheric pressure and 273 Kelvin. So, what I want to say from here is that you can get so many information. You can also get the information what will be the amount of oxygen that will be required for this reaction, and hence what will be the amount of air that will be required to convert 1 ton of met into copper. So, you can straight away calculate from here the moles of oxygen, that will be 3.77 plus 6.8175. You divide by the composition of air, and in that the oxygen is 0.21%. So, if you divide, you get the moles of air. So, you can get, what I mean to say, you can get so many information from the balanced chemical equation. That was the idea of solving this particular problem. Now, let us take another thing, the ideal gas law. For gaseous purposes, this is also very important. Ideal gas law. Now, most gases that are taking part in our metallurgical processes, say for extraction and refining, they are at high temperature. Say typically pyrometallurgical extraction of metals, it involves a very high temperature ranging from anywhere 1000 to as high as 15 or 1600 degrees Celsius. So, the gases, they follow the ideal gas behavior, that is PV, that is equal to N R T. All of you know, not very big thing I have told you. Now, so here we can say 1 kg mole of gas, 1 kg mole of gas, that is equal to 22.4 meter cube at 1.01325 atmosphere into 10 to the power 5 Newton per meter square and 273 Kelvin. That is all known to us. Also 1 pound mole of gas, 1 pound mole of gas, that is equal to 359 feet cube. I think I had given elsewhere, but anyway this also as an information. Now, from here we can also write down say V upon N, that is equal to R T upon P, and this is meaning that at any given temperature and pressure, at any given temperature and pressure, volume per mole, volume per mole or number of moles in a given volume is same. This is sometimes you do require for calculation of material balance problem involving in metal extraction and refining. Now, just to close the lecture, I would like to tell you that in gas mixture which are consisting of ideal gases, each component of the mixture it also follows the ideal gas law. So, for ith component of an ideal gas of an ideal mixture contained in a volume V at temperature T, we can write down P I into V, that is equal to N I R T, where P I that is equal to partial pressure of that particular component, partial pressure, and N I is the number of moles of that component. So, ideal gases they follow Dalton's law, and Dalton's law is simply states that total pressure P T that is equal to 1 to N P I. So, this Dalton's law is also very important in case of gases which are having the mixtures of several components.